Okay, so hello everyone. So really, we are coming back to Chemistry Olympiad training. Today we'll be looking at set number 5 and 6 in the same session, probably. Okay. Now, since the Sec 3s have already learned atomic structure, this will be a good revision for all of us on what is inside an atom. So I'm sure you know by now, atoms contain protons, electrons, and neutrons. All right. So over here, the P plus represents protons, the E minus represents electrons, and of course, the N here represents neutrons. Okay. So these are the three subatomic particles that you should already be familiar with from your study of atomic structure. Of course, these three types of subatomic particles differ in terms of their charge and their mass. So one of the first things that scientists discovered was that protons, electrons, and neutrons, they have different charges and different masses. One way to experimentally prove that is to subject these particles to the influence of an electric field. Electric field literally means I put them between two parallel plates. One plate is positively charged and the other plate is negatively charged. Obviously, the electron is attracted to the positive plate, right? That makes perfect sense. Okay, the negatively charged electron should be attracted and deflected towards the positive plate. All right. On the other hand, the protons are deflected towards the negatively charged plate. Okay, this makes perfect sense. I think what needs more examination are the angles of deflection. So the angles are given this symbol theta. So the angle of deflection, theta, clearly doesn't seem to be the same here and, and here, right? So you can see that the angle of deflection for a proton is smaller than the angle of deflection for an electron. So we can say protons are deflected less than electrons. So scientists discovered this. Why is it the angle of deflection is different for a proton and electron? There must be a reason why. Well, the simple reason why is really mass, right? Electrons will be deflected much more than protons because electrons are much smaller in mass. Okay, you must remember, right? Electron, the relative mass is 1 over 1840. So from this alone, you can already tell electrons are 1840 times lighter than a proton. Okay, so scientists discovered, okay, so the angle of deflection is proportional to the charge over mass ratio, or what we call the charge to mass ratio. Okay, and with that, I'm sure you can predict which particle will be deflected more. So let's quickly do question 1. To do question 1, I need to work out the charge over mass. How do I know the mass of lithium? To find the mass of lithium, I go to the periodic table, I search for lithium. There are two numbers. The larger number is the one that is the mass. So the mass of lithium, the relative mass of lithium is 7. Okay. So with that, we can easily work out for all of them. May I give you all about 2 minutes to work out which particle will be deflected more? Remember, it's related to the charge to mass ratio. So let's take 2 minutes to work out 1A, 1B, 1C. Give me just 1 minute more to finish question 1A, 1B, 1C. Okay, I'm sure all of you have worked it out. If you work out the charge to mass ratio, the one with the larger value for the charge over mass will have a larger deflection in an electric field. So in the case of lithium and sodium ions, lithium has a larger charge to mass ratio. Okay, so it's 1 over the mass 7 versus 1 over 23 for sodium. Next, we come to the negative ions. Now, we do not substitute the negative in. We are just interested in the magnitude of the charge. Meaning, instead of substituting -1, we're going to substitute 1. So for F minus, it will be 1 over 9. O2 minus will be 2 over 8. 2 over 8, sorry. 19, sorry. 1 over 19 and 2 over 16, sorry. All right. So the idea is we do not substitute the negative in. We are just interested in the magnitude of the charge. Okay. So I'm sure you can evaluate 2 over 16 is a much larger charge to mass ratio. Therefore, O2 minus is deflected more. Okay. And finally, for the very last one, Mg2 plus ion will be deflected more than K plus. All right. And with that, we conclude the first section of this set of notes, which is good news. All right. Now, the second section, which I trust you remember, is about proton number and mass number. So, proton number is the number of protons in the nucleus of an atom of the element. So, proton number is also known as the atomic number, and that is the smaller number of the elements in the periodic table. So, in the case of iron has a proton number of 26. So iron has 26 protons. If iron has 26 protons, it also has 26 electrons in its atom. Because atoms are electrically neutral, so the number of electrons is equal to the number of protons. Okay? That's for an atom, not an ion. We'll see very soon, ions are not like this. Ions basically are particles formed after the atoms lose or gain electrons. Okay, so in an ion, the number of electrons will no longer be the same as the number of protons. Finally, what is the larger number for the element? The larger number is the mass number or the nucleon number. So the mass number is defined as the total number of protons and neutrons in the nucleus of an atom of the element. So P plus N equals 56 in this case. So since iron has 26 protons, that means it has 30 neutrons. We take the bigger minus the smaller. So this one you learn in Sec 1. You may have just memorized it, but let's learn to appreciate the definitions a lot more. Moving on, I think Miss Asma has also gone through this. I hope you know sodium is 281. I will not belabor the point. Okay. Now, since Miss Asma has already finished electronic configurations, I will also skip this. All right. I will skip all the drawing and go straight to this. Okay. Let's go to page 5. Okay. For the Sec 3s, we want to practice drawing later. Okay. Miss Asma should have gotten onto this in class. Now, on page 5, you see the link between electronic configuration and the position of the periodic table. This is very important. It's probably one of the most important lessons you can have in the whole of chemistry. Chemistry is all about electrons. To be really honest, we are not really interested in protons and neutrons. That's why you noticed I did under the segment on radioactivity, set number 2. That is the only time we will actually look at protons and neutrons when we look at radioactive decay. Other than that, right, we will never ever focus on protons and neutrons. Chemistry is entirely about electrons. You could go to university and do chemistry in university, and you will still be writing electronic configurations, and you will still be learning about electronic configurations. Electronic configurations literally determine every single thing in chemistry, whether something is reactive or not reactive, whether something will explode, whether something will be stable, whether something will react with oxygen. All that depends on simply electrons. Where are the electrons? How are the electrons arranged? This is why, okay, for the Sec 3s this year, I made it a point to teach electronic configuration in Sec 1, because electronic configuration is the most important thing you can ever learn in chemistry. So I hope as Miss Asma went through electronic configuration, you remembered that Madam Afana, Mr. Song, Miss Cheong, myself, we have taught you this in Sec 1, and we have taught you group and period as well in Sec 1, because this is the most important concept. I cannot stress this enough. Okay, even when you go on to A level or university, electronic configuration is still the most important thing you can ever remember and learn. All right, so I've did so much. What is the electronic configuration for fluorine? Fluorine has 9 electrons, so it's 2, 7. Chlorine, 17 electrons, 2, 8, 7. So what is similar about them? Immediately you realize the 7 is similar, right? So we say that they have 7 outer shell electrons, 7 outermost electrons, or more commonly, 7 valence electrons. So fluorine and chlorine, they have the same number of valence electrons, 7. So valence means outermost. Okay? Now the actual meaning of the word valence refers to the number of electrons it can use for bonding. So what we mean to say is that, oh, chlorine can actually, in theory, use up to 7 electrons for bonding, even though it may not use all 7. Okay? So in short, valence actually refers to the outermost electrons which can be used for bonding. Okay? Now, so the 7 valence electrons tells me that both elements are in the same group, and this is group 17. All right? So elements in the same group will have the same number of valence or outermost electrons. And the rule here is group 1, 1 valence electron. Group 2, 2 valence electrons. Group 13, 3 valence electrons. Very important, once you get to the teens, we just want the last digit. 13, 3 valence electrons. 14, 4 valence electrons. 17, 7 valence electrons. All right? Important concept. You must be able to get this. Okay? I'm actually going to do this with my combined science class tomorrow. I have called it the most important chemistry lesson you will ever have. Okay? So I hope you realize the number of valence electrons will tell you which group the element is from. Please be careful with the teens. 13, 3 valence electrons. 14, 4 valence electrons. 15, 5 valence electrons. Group 16, 6 valence electrons. And finally, group 17, 7 valence electrons. Okay? Next, we go to fluorine and neon. Fluorine and neon. Fluorine is 2, 7. We did it just now. Neon has 10 electrons. So it's 2, 8. So what is so similar about these two? The idea is both have 2 shells. First shell, second shell. First shell, second shell, right? So both atoms have 2 electron shells that have electrons in them. So we say they have the same number of filled electron shells. Notice I said filled, I didn't say fully filled. It's okay if the shell is not fully filled. They have 2 shells that are filled to some extent. All right. So elements in the same period have the same number of filled electron shells. So period 1, 1 shell. Period 2, 2 shells. Period 3, 3 shells. Period 4, 4 shells. And so on and so forth. All right. So with these two concepts, you have already learned how the entire periodic table is organized. You have learned the logic behind the periodic table. Now, I don't want to bring in isotopes now. Isotopes are not very important. Remember, isotopes, I think Miss Asma covered in class, same number of protons, different number of neutrons. Protons and neutrons are boring for chemists. Let's not talk about them. All right. So isotopes are in the syllabus, but it's more of a side note. Electronic configuration, let's be disciplined. All isotopes of the same element will have the same electronic configuration because isotopes have the same number of electrons, right? So today we are just going to focus electrons, electrons, electrons. Protons and neutrons, leave it aside, okay? Now finally, neon and argon, I think you know. I think you have written out the electronic configuration. Neon is 2,8, argon is 2,8,8. So we can see, hey, they have 8 electrons in their outermost shell. We call that a fully filled outermost electron shell. Okay. Now, the key thing about neon and argon is that their outermost electron shell are fully filled. And therefore, that makes them very stable, very unreactive. So you have learned one more thing. If your outermost shell is fully filled, you become very stable, very unreactive. This automatically means anything that doesn't have a fully filled outermost electron shell is very reactive. That means, for example, fluorine. Fluorine is 2,7. 2,7 is going to be super reactive because the outermost shell is not yet fully filled. Similarly, sodium, 281. 281, 1 is clearly nowhere near fully filled, right? The outermost shell. Therefore, sodium is very reactive. Okay, so what makes something reactive? Something is reactive when its atom does not have the fully filled outermost electron shell. This is why electronic configuration is so important. From this alone, I can really tell that sodium is very reactive. Sodium will explode. Fluorine, very reactive. It's going to explode. Okay? Now, so the fully filled outermost electron shell is the key. Every single atom will want to achieve this. This is like the goal of every single atom. I want a fully filled outermost electron shell. And in the case of the second shell and third shell, that is 8 electrons. So 8 is the magic number for the second shell and the third shell. In order for the second shell to be fully filled, that's 2 electrons. In order for the third shell to be fully filled, it's 8 electrons for O level. Up until calcium. O level stops the study calcium. Beyond calcium, that's what we're going to discuss in the second half of the year. Okay, so what I'm going to tell you today is a mixture of O level and A level. Does it mean that O level is wrong? No. It just means that at A level, you will learn more sophisticated models that will bring you further. So at O level, we generally say that for the third shell to be fully filled is usually 8 electrons. Usually. All right. So every single atom will want to do something to achieve fully filled outermost electron shell. That is to achieve 8 electrons. How will they do that? And that brings us to 3 flourish. Your HBL on Monday is on ionic bonding. And this is what you're going to be doing for HBL. So I'm covering with you now. So atoms that do not have a fully filled outermost shell will do all they can to achieve the fully filled outermost shell. What can they do? Well, for example, for sodium, sodium is 281. Clearly, that's not fully filled outermost shell. How about let's just lose the 1 valence electron. By losing the 1 valence electron, sodium becomes 2,8. Right? Now, that has achieved a fully filled outermost electron shell, hasn't it? Okay? So, the crucial thing is by losing one valence electron, the sodium atom can actually achieve a fully filled outermost electron shell. The only catch here is you lost one valence electron. Do you also lose protons? The answer is no. So at the start, there were 11 protons and 11 electrons. After losing one valence electron, it now has 10 electrons. 11, you lose one is 10, right? But the protons remain the same. The protons are not lost. The protons remain the same. That's why for chemistry, protons are boring. Protons are never ever lost during a chemical reaction. Protons can only change in number if there is a radioactive decay, which this is not. This is a chemical reaction. Okay? So protons will always remain the same in number. Protons are positive, electrons are negative. I'm sure quick mathematics will tell you, hey, this is now going to have a 1 plus charge. And indeed, that's why we say sodium has now formed the Na plus ion. The plus is written on the top right hand corner as a superscript. We say that sodium is now a positively charged ion with a 1 plus charge. We do not write the 1, just like algebra, you don't write 1x, you just write x. Same here, 1 plus, we just write plus. Okay, so why has it formed a positive ion? Because sodium atom has lost one valence electron. When you lose the negative electron, you will become positive. Okay, the analogy I always give, there are so many negative things in our life. If I lose the negative things, I become more positive. Exactly. If I lose one negative electron, I become positive. Okay. So now, very quickly, magnesium. Magnesium is 282. Again, 282 clearly is not fully filled outermost shell, right? 2 electrons in the outermost shell, that is not fully filled. So what will magnesium do? Magnesium loses 2 valence electrons. By losing 2 valence electrons, magnesium will achieve 2,8. Right? But now you know, if I lose 2 electrons, clearly it can no longer be electrically neutral. Just now, sodium lose 1 electron, becomes 1 plus in charge. Now, you can imagine, because it has lost 2 electrons, it will become 2 plus in charge. Okay, so magnesium forms Mg2 plus ions. So what is an ion? An ion is a charged particle. It must have charge. An ion is a charged particle formed by losing or gaining valence electrons. In this case of magnesium, magnesium loses 2 valence electrons, therefore it forms the Mg2 plus ion. Okay? Now we can go one step further. We can even generalize sodium and magnesium. Sodium and magnesium are examples of metals, right? They are metals. So in general, metals lose valence electrons. Therefore, metals form positive ions. Positive ions are known as cation ions because there's a T, the T is like a plus. So cation ions are positively charged ions. Okay? So that's metals. How many metals are there in the periodic table? If you look at the periodic table, there are 118 elements, right? Out of the 118 known elements, the majority are metals. The majority. Okay, I would estimate about 70% are metals. Okay, so sodium, magnesium, they are metals, but so is aluminum, so is iron, so is copper, so is potassium. So there are many, many metals. In general, metals will form positive ions because they lose valence electrons. On the other hand, non-metals such as chlorine. Chlorine has an electronic configuration that is 287 in its atom. Because it's 287, clearly the outermost shell is not yet fully filled. So what can chlorine do? Chlorine will have to gain one valence electron, right? Instead of losing 7 valence electrons, which will require a lot of energy to lose 7 valence electrons, how about just gain one electron from somewhere, right? If I were to gain one valence electron, it will achieve 288. Again, 8. Lucky number 8 makes the outermost shell fully filled. So, of course, this allows us to conclude non-metals like chlorine will gain valence electrons. And because they gain these negative electrons, they become negatively charged. That's why chlorine forms Cl minus. You gain one electron, negatively charged. Now, Cl minus is called chloride ion. Chloride ion is Cl minus. Chloride is not the same as chlorine because chloride is after it has gained an electron. After it has gained an electron, it has a fully filled outermost shell. So chloride is stable. Chlorine, not stable because it has yet to achieve a fully filled outermost electron shell. Okay, so not just changing the spelling, just by gaining a valence electron, it becomes stable, and that makes all the difference. Okay. Next, where did this electron come from? Where did this one valence electron that chlorine gained come from? Must have come from somewhere, right? It can't drop from the sky, right? So clearly, this is two different elements. One is losing electron, one is gaining electron. The exciting part is what happens when the two elements come together. Chlorine has to gain one electron. Isn't it just perfect that sodium loses one electron? That's perfect, right? So if sodium and chlorine could come together, bond together, sodium loses one valence electron. That one valence electron will go to chlorine, which gains that one valence electron. So in short, metal like sodium will transfer the valence electron to non-metal like chlorine. And that, ladies and gentlemen, is how chemistry works. Chemistry works by moving electrons around. In this case, moving the electron from sodium to chlorine, from metal to non-metal. And for my 4 flourish students, you have seen so many examples of electron movement, from metal to non-metal, from more reactive metal to less reactive metal, right? For flourish, that's how the electric cell works. Now, if you look back, isn't it all about electrons? The electrons just need to move from somewhere to somewhere. And there's a logic behind it. In this case, metals lose electrons, non-metals gain electrons. Okay? And so, if sodium and chlorine come together, they form sodium chloride. And now you can see why sodium chloride is NaCl. Sodium formed Na plus because it lost one electron. Chlorine forms Cl minus because it gained that one electron. Isn't it just perfect? Okay. Next, you will hear a lot of people say in their daily lives, oh, I must reduce my sodium intake. Chinese New Year is coming, right? During Chinese New Year, a lot of people like to eat steamboat. Steamboat is high in sodium. But is it really high in sodium metal? Is it really shiny sodium metal that you throw into the steamboat? No, please don't ever throw sodium metal into the steamboat, okay? You can't eat sodium metal. Sodium metal is not stable. It's not stable because it's 281. So sodium metal is not stable. What happens is sodium will react to form compounds like sodium chloride. So what you are eating in the steamboat is sodium chloride, which contains Na plus ions, Cl minus ions. Okay. Similarly, if later on you go to your toothpaste and you look at the label, you will see the word fluoride. I'm sure you can make a good guess. What is fluoride? Fluoride is F minus. Okay? It's F minus, not F. You can't eat fluorine. If you eat fluorine, you will explode because fluorine is 27. 27 unstable. Don't have fully filled outermost shell. But F minus is different, right? F minus means my 27 has gained 1 electron, is now 28. 28 is stable, fully filled outermost electron shell. That's why the fluoride is stable enough to be put into your toothpaste. Okay? Can? So fluorine, fluoride. Chlorine, chloride. They are not the same things. Similarly, oxygen. Oxygen is 2, 6 because oxygen has 8 electrons. So 2, 6 is the electronic configuration for an oxygen atom. Okay, so atom is what is started from, information you get from the periodic table. All right, obviously the oxygen atom is not stable in any way, right? It doesn't have a fully filled outermost shell. So what do you think oxygen will do? An oxygen atom, in order to achieve a fully filled outermost electron shell, has to gain. Gain how many electrons? Remember, magic number 8. So it needs to gain 2 valence electrons, and that makes 2, 8. And because of that, now it can no longer be electrically neutral. If it gains 2 electrons, it will form a 2 minus charge. So this is the oxide ion. Okay, so you notice the negative ions, their names will almost always end with IDE. Chloride, oxide, fluoride. Okay, and with that, we come to the next 2 pages. Now, I'll advise the 3 Florist students to work through these 2 pages. I'm not sure if it's in your notes, but do work through these 2 pages yourself, especially during the HPL for your Pure Chem next Monday. These 2 pages are the most important pages in the whole of your study of chemistry. Okay? Now, I'll skip these 2 pages and I'll go straight to the A-level stuff. So that's where the O-level Pure Chemistry ends. And now let's continue from where the O-level Pure Chemistry ends. If you go on to JC, or if you go on to Poly and do a chemistry-related course, the lecturer will almost always say this statement, which I do not agree with. Oh, what you learned at O-level was wrong. It's not wrong. Okay? What you learned at O-level is not wrong. It is just a different, a more primitive, older fashioned model. Okay? At O-level, you have learned about shells. First shell, 2 electron. Second shell, maximum 8. Right? So you learn things in terms of shells. However, clearly the world is not so simple. It is not as if the atom was like onion, no? 1 layer, 2 layer, 3 layer. An atom does not actually behave like this. The shells are just convenient concepts for us to organize our understanding of electrons. All right. The reality is, at A level, you will learn that each shell is further divided into subshells. And that is the key. So for the 4 Flourish students, I hope you remember some of this. So this is the new stuff you need to pay a full attention already for Flourish. So each shell, first shell, second shell, third shell, they are further subdivided into subshells. Okay, and this is where you need to follow me. Now this table looks complicated. Let me explain to you. Now the first shell has the subshell called 1s. When we write 1s, what we mean is this is the first shell. The number in front refers to first shell, second shell, third shell. So the first shell, therefore, the subshell is 1. S is the type of subshell. There are, broadly speaking, 4 main types of subshell. S, P, D, F. Okay, I repeat. There are 4 types of subshells. S, spdf. Okay, these are the main ones that we will deal with today. So, first shell only has one S subshell. This means it's the shell from the first shell. Okay? So the number in front is not telling you how many. Number in front is the first shell, second shell, third shell. Okay? Now, the S subshell only holds 2 electrons. I repeat, the S subshell holds 2 electrons. That's why, because the first shell only has the one S subshell, it can only hold 2 electrons. That's why first shell, 2. Can? Now, the second shell is where it gets a little bit more exciting. We have the 2S subshell. 2S, does it mean 2 times S? No, it's not 2 times S. No, no. 2S is not 2 times S. It's not multiplication here. Remember, the number in front refers to which shell is from. So 2S refers to the S subshell from the second shell. And because it's a S subshell, it also holds 2 electrons only. So S subshell always holds 2 electrons maximum only. Doesn't matter which shell it's from, so long as it's an S subshell, it will always hold 2 electrons. But the second shell is bigger. The second shell, besides having the 2S subshell, it also has the 2P subshell. Again, is it 2 times P? No, it's not. 2P means the P subshell from the second shell. Now, P can hold 6 electrons. So 2P holds 6 electrons. So the second shell has 2S and 2P subshell. And that's why when you add them up, 2 plus 6 equals 8. That's why at O level, we taught you second shell holds maximum 8 electrons. Okay, I think so far so good. Are we all right? If you're all right, can you give me a reaction button, emoticon? No reaction? Oh, okay, we are all right, Okay, my fourth flourish, are we all right? Fourth flourish, no reaction, is it? Are we coping with this fourth flourish? My own student? Yes. So, I'm sure you can see a pattern coming up soon. The third shell being even further away from the nucleus, being even bigger, the third shell should hold more subshells, right? In particular, the third shell has 3S, 3P, 3D. Okay, so 3S means S subshell from the third shell. That's why, because it's S, it holds 2 electrons as well. 3P subshell is the P subshell from the third shell. P subshell holds 6 electrons. How about D? D holds 10. Wow, there's a pattern, right? This is a number pattern, right? So S is 2, P is 6, D is 10. 2, 6, 10. I'm sure you can see a pattern. Okay? So basically, every single subshell, S to P to D, is 4 more electrons. All right? So being the third shell, it only has 3S, 3P, 3D. S, P, D, F, right? So being the third shell, it has S, P, and D. Therefore, if you add up 2 plus 6 plus 10, it's 18. So the third shell actually, in theory, can hold up to 18 electrons, not 8. So why did O level teach 8? O level taught you 8 because you have not learned subshells. Therefore, you wouldn't know that the subshells are filled 3S and 3P first. After you finish filling 3P, you need to move on to the fourth shell first, then come back to 3D. That's why O level cannot go into this level of complexity because you have not been taught subshells and it'd be too complicated to teach this over the period of time that you have at O level. Okay? So are we okay with the third shell so far? Third shell actually can hold up to 18 electrons. Okay, so even though third shell can hold up to 18 electrons, we say that if it can fill the 3s and 3p, that's already considered fully filled and stable. All right. So even though it only has 8 electrons in the third shell, we consider that stable. Okay. All right. So 288 is considered fully filled, even though it's just 8 electrons in the third shell, because it has filled up the 3s and 3p. All right. So I've answered that question. Now, finally, the fourth shell has 4s, 4p, 4d, 4f. I'm sure you can see 2, 6, 10, and finally 14. Adding up together, the fourth shell can hold up to 32, you know. And yet, if the fourth shell can fill 8, it's also considered stable. Okay? So 8 is indeed a magic number, a lucky number. Now, why so mysterious? How come it can fill up to 18, fill up to 32? How come if I feel 8 already stable already? That has to do with the ordering of the subshells. In what order do you fill the subshells? And this is called the Aufbau principle. The Aufbau is a German word. Okay? The German word is aufbauen. Aufbauen is the German word, the verb to build up. Bauen is to build. Auf is up in German. So aufbauen is to build up. We are building up the atom subshell by subshell. Okay? So how do you build up the atom? You start from the one that is closest to the nucleus. That one I think you know from Sec 3. So now everyone take a pencil or pen and follow what I'm doing. There's some space on the left. Use the white space now to do this. We are going to basically do what you see on the paper already, but do it with me. Fill up 1s first. 1s is the lowest because it's closest to the nucleus. All right? Above it, we're going to write 2s, 2p this way. Then 3s, 3p, 3d this way. We're going to write row by row. 4s, 4p, 4d, 4f this way. 5s, 5p, 5d, 5f. And you must be wondering what comes after f, right? After f, it follows the alphabetical order. So f, then g. 6s, 6p, 6d, 6f, 6g, 6h. All right, so today we only need up to 6. Thankfully, we only need up to 6 shells. Okay. So now, using a different colored pen, okay, you have a green pen or something, let's draw arrows. First arrow, how do you draw the arrow? We start from the empty space and draw up. The first arrow goes through 1s. That is the first subshell to be filled. The second arrow goes through 2s. So we have 1s, then 2s. Notice how all the arrows are diagonals. We're going to use diagonal arrows. Next, diagonal arrow. Oh, what do you see? The diagonal arrow now crosses 2p, 3s. 2p, then 3s. The next diagonal arrow, empty space, draw up. Oh, wow. So now it has crossed 3p. And after 3p, shockingly, 4s. Right? Because the diagonal arrow joins 3p and 4s. So I'm just writing it out. Okay? Next diagonal arrow. Oh my gosh. You mean it's going to go 3d, then 4p, then miraculously 5s? Indeed, it is. That's the order. Okay? It doesn't even care about the 4D, 4F. It will go to 5S first. Okay, next diagonal arrow. Wow, the next diagonal arrow is 4D. That's weird. Then 5P. Then 6S. So do you start to see at higher shells, you don't feel shell by shell. You really feel subshell by subshell. And the subshells that you are feeling may not be from the same shell, you know. Do you notice how I'm feeling like 4P, 5S? Oh, 4P, 5S means what? I go to the P subshell of the fourth shell. Then after that, S subshell of the fifth shell. Then come back D subshell of the fourth shell again. Indeed, that is the order. All right. Okay. Now we'll go on to the last few arrows. Let's finish with the 4F one. We need the 4F one today. All right. So after 6S, we go back to 4F. You know, wow. After 4F is 5D. After that, it's 6P. Okay. So it's very, very interesting how the subshells are being filled. Okay. Any questions about how to draw these diagonals? Yep, indeed. If the next subshell to fill is not one of the subshells in its shell, it's stable. Yeah, indeed. That's right. So long as you fill 4P, or so long as you fill 3P, it's stable. Yeah. So long as you fill 4P, it's stable. Okay. And that's why O level, we can only test you the elements up to calcium. Because up to calcium, all right, that's where the rule will break down. After calcium, you will need these subshells to write the electronic configuration. Okay. Now, Mr. So has given you iron over there. So iron is a interesting element. Okay. So I guess we shouldn't do iron. I should challenge myself to do something more complicated. Okay. So being a chemistry teacher, I should challenge myself to do something really complicated. I might regret this. Okay. Let's do this element called neodymium. Can anyone find neodymium? What is the chemical symbol of neodymium? Someone type in the chat or the Q&A. What's neodymium? We found it. ND. So ND has 6T electrons. I hope I got it right. Okay, this is a mammoth number. My fourth flourish will know we have never written electronic configuration for anything even somewhat close to this. Okay? The last time I wrote this electronic configuration was like in university in my third year, probably when I was learning the last two rows of the periodic table. Okay, in case you're wondering, I still learn the periodic table in university. At O level, you learn the basic one. At A level, you learn the middle block called the transition metals. At university, third year, you will learn the last two rows, and the last two rows are the wow, interesting. Okay, so now let's do neodymium, shall we? Let's do it together. Please prepare space. You need space. Mr. So also needs space. Okay, I'm a bit nervous because I feel like I'm going to make a mistake soon. There's so many electrons. So let's start. 60. Please count for Mr. So. If Mr. So makes a mathematical error, alert Mr. So because I don't have a calculator with me. First, we start with 1s. 1s is S subshell can only hold 2 electrons. We say 1s2. Notice how it's not square, it's not squared. This means 2 electrons in the 1s subshell. So the number of electrons is written as a superscript above the subshell. So 1s2. We don't read this as 1s squared, it's 1s2. After 1s is done, what's the next shell? The next subshell is 2s. Again, s, right? S is always 2. So 2s2. After that is 2p. How many electrons can 2p accommodate? 2p, if you refer to the previous page, the pattern was 2, 6, 10, 14. So p is 6. So 2p 6. After 2p is 3s. 3s 2. Because s is 2. After 3s is 3p 6. Okay, so far so good, huh? And then we come to the weird crossovers. The first weird crossover is after 3p is 4s. This is where please leave a blank because we have our poor friend, our pure friend 3D hasn't gone in yet. Leave a blank and write 4s. So even though we fill 4s first, you must remember when you are writing things out, you must leave a blank for the poor subshell 3D, which has not received airtime yet. Okay, so 4s2. After 4s, then you come back to 3D. 3D, D can hold 10. Okay? After 3D is 4p, right? So if you look just down order, 3D then become 4p, so 4p6. So how many already? 2, 4. Oh my gosh. Can someone quickly add up the numbers and tell me how many electrons this is? 10, 18, 28, 36. 36. Okay, so unfortunately, I have 60 electrons. This means Mr. So has 24 more electrons to go. I'm getting nervous. Okay, so after 4p, what's next? Hello? After 4p is? May I know what's next? From the order that we did just now, 5s. So 5s. S is 2 again. Oh, Mr. So made a mistake, right? Cannot write 5s, must leave blank. Remember 4d, we still have 4f. We must give them airtime, okay? Must give them airtime. So 5s2. After 5s is 4d, that's 10. Okay? Now, do you realize after 4d is not even 4f yet, no? It's not even 4f's turn, you know. After 4d, we go on to 5p, right? So the next one to fill is 5p6, you know. How many electrons is this already? I'm getting nervous. 18, right? So 36 plus 18, right? How much is 36 plus 18? 54, is it? Okay. So far I've written 54 electrons, but neodymium has 60 electron. So how? I still got 6 more. How? So now I'm at 5p already. 5p already. What's next? Is it 4f? No, it's not. After 5p is 6s. 6s2. And finally, after 6s, then I come back to 4f. So now can someone tell me how many electrons should I put on 4f? Answer, please. How many electrons are in 4f? 4, yes. So when you add up the number, must add back to 60, okay? So indeed, neodymium is 4f4. And I know it's 4f4, by the way. Okay, I pretended to be dramatic and everything. It's not so dramatic. It's very easy to tell. All right, so I hope you have copied. Now, if you go to the last page where the periodic table is, I know it's 4f4 because it's the fourth element of this series. Okay, it's the fourth element of that series. So the first element is 4f1. So lanthanum will be 4f1. Cerium will be 4f2. Praseodymium 4f3. And neodymium 4f4. Okay, so even though I was dramatic, but yes, I know it's 4f4 actually. Okay, so I actually know how to check my answer. Okay, so that was neodymium. Now, how is neodymium useful in your life? Neodymium is one of the rare earth metals. You have heard this word rare earth metals a lot in the newspapers in particular, because different countries are trying to fight over the reserves of the rare earth metals like neodymium found on Earth. Now, rare earth metals are not really rare, okay? They are actually quite easily found around us. Rare earth metals are not rare. They are called rare earth metals because it's rare to find them in their metallic elemental form. Most of the time, neodymium and the other rare earth metals are always in their compound form. For example, you might find neodymium as neodymium oxide. Okay? Extracting these metals from their compounds is hard. Very hard. That's why it's called rare earth metals. They are not rare, they're just difficult to extract. Okay? But the sad thing is neodymium is one of the most important metals for your TikTok and Instagram. Without neodymium, I cannot imagine modern electronics surviving. Because almost every single electronic appliance has a magnet in it. And the best magnetic materials are not iron. I'm sure you know iron is a magnetic material. You can attract it using magnet and blah, 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 right? But iron is not the best magnetic material. The best magnetic material that is used to make modern magnets is almost always praseodymium, which is next to neodymium, or neodymium itself. All right. So it's very difficult to extract neodymium because, number one, it's very difficult to separate it from other metals. Okay, so even if you can extract it easily, you could not separate it from other metals. There's no separation technique you can use. You can't use filtration, you can't use distillation for that matter. Okay, yeah, so that's neodymium. Okay, so now I've digressed. Now we need to practice writing the electronic configuration. May I suggest, in the interest of time, let's do A, E, F, G. A has 11 electrons. Should be simple, but EFG is more exciting. Can we please take 5 minutes to start? I love G. G is terbium. Terbium has 65 electrons. Having said that, if you have done neodymium 60, I guess 65 should be easy. All right, so let's start AEFG now. Okay, I hope you are looking rigorously at the order of the subshells. Okay, must try. This is one of the most exciting and important atomic structure lessons. Okay, it's okay if you don't understand everything, but it's good to practice trying to write electronic configurations in the spdf format. Okay, so that later on when you go to, let's say, YIJC, right, for the Sec 3s, at least you will know what the chemistry teachers are talking about over there. Which reminds me, if you want to sign up for the JC visit, do that soon for the 3 flourish students. Okay, I hope you are already on bromine, hopefully. You should already be on bromine, which has 35 electrons. Well, 35, right? That's a lot. Okay, I'm going to write the answer for sodium. Sodium is much simpler. Sodium 1s2, 2s2, 2p6, 3s1. All right, so that's sodium 1s2, 2s2, 2p6, 3s1. Okay. Can I check, is everyone on bromine now at least? Are we on bromine already? I hope so. If you're on bromine, can you give me a reaction button, please? Bromine. We are on 35, right? I hope we have finished the titanium, the 22. Titanium is a useful metal. Okay, those of you who ride bicycles, you may know titanium bicycles are the most expensive bicycles. All right, bicycles can be made of many materials. I mean, any lightweight material would work. But besides being lightweight, you will want your bicycles to be strong, right? So the best option is actually titanium. Titanium is lightweight, strong, and also resistant to rusting and corrosion. That's why titanium is very, 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 very popular as a material for making bicycles. For titanium, let me give you the answer, and you can check your answer. Okay, titanium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. Wow, Mr. So is so fast. How did Mr. So arrive so fast at this? Okay, so that's titanium, sodium. Okay, let's do bromine. Okay, so I hope you have had a chance to try bromine 35. Okay, after some time, you'll see a pattern, and that's how you write very fast. So, for example, Mr. So knows if I fill 1s to 3p, that's 1s2, 2s2, 2p6, 3s2, 3p6, that's 18. I know that's 18. All right. So, given that it's 35, I know it will go to 4s2 and it will have 3d10 and it will 3p5. Okay, so bromine is 1s2, 2s2, 2p6. Oh, so not 3p5, 4p5. What am I talking about? 4p5. Right. So, it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p5. All right. So you should be able to do that. Terbium is the only one that's really difficult. I'm going to copy my previous page. Okay. Terbium shall be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f, 36 plus, wait, 4f9, 5s2, 5p6, 6s2. So that's terbium. Terbium is really long. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p. Okay. I got 4f9 so quickly because I just added 5 to the 4f4 in neodymium. Okay. Because terbium has 5 more electrons than neodymium just now. Okay, so what is the whole purpose of doing this? Now with SPDF, you can start to see, oh my gosh, this is how things are gonna work, you mean? Yeah, indeed. Now, I hope we have finished. Okay, now let's look back on sodium. Now we have about 10 minutes left. I'll just finish with this. Okay, I won't go on to set 6. Set 6, we can do it next lesson. Now, sodium, if you now group them according to shells, not subshells, are shells. So first shell, second shell, third shell. What do you see? First shell 2, second shell 8, third shell 1. And we back to the 281. Sodium is 281, right? That's what you have learned in class. So indeed, the SPDF model is not incoherent and misaligned with the O-level model. It's the same model, actually, ultimately. They still lead back you to the same conclusion. SPDF is in terms of subshells. 281 is simply in terms of shells. How about titanium? Titanium is interesting. 2, 8, strangely, 10, 2. All right. How about bromine? 2, 8, 18, 7. Wow, bromine should have 7 in the outermost shell, right? Because bromine is in group 17, just like chlorine. Okay? And of course, for terbium, it's much more complicated. I'm sure you can imagine. 2, 8, 18. And then the fourth shell is like 2 plus 6 plus 27, 8, 2. So it's like, wow, weird, right? Now, what's the point of writing in terms of shells then? So you realize that writing in terms of shells is helpful when you are dealing with elements that are relatively small, don't have so many electrons. That's why at O level, you stop at calcium. You stop at calcium because that is where the limit where you don't need subshells. Beyond calcium, such as titanium, you will already need subshells in order to write the electronic configuration. All right. Now, beyond that, I want you to take note. What was the last subshell you filled? For sodium, the last subshell you filled was 3s. For titanium, what was the last subshell you wrote? The last subshell you wrote is 3d for titanium. For bromine, what was the last subshell that you wrote? Definitely the 4p, right? And finally, for terbium, what was the last subshell that you filled? It's the 4f. Okay? If you look at the periodic table, Mr. So's drawing is no good, Mr. So's drawing is no good, The periodic table looks like this. Where would you find sodium? Sodium is found here. Where would you find titanium? Titanium is found here. Where would you find bromine? Bromine is somewhere here. Where is terbium? Terbium is somewhere here. This block is called the S block elements. They are called the S block elements because the S subshell is the last one to be filled as you write their electronic configurations. So this block is the S block. S block is group 1 and group 2. Then we move on where titanium is. Titanium is called the D block elements. Why D block? Because the D subshell is the last one that you filled. So D block elements are what you call at O level transition metals. Even though it's not 100% the same, transition metals are actually a subset of D block. Okay, but that one you will learn later on. Next one, where bromine is, what block do you think this is called? Bromine, the last subshell that you filled is P block. It's P, right? So on the right hand side is P block. And I'm sure you can predict. How about where terbium is? That's called F block. S, P, D, F. All right. Now at O level, you learn the S block, group 1, and you learn the P block, group 17. Okay. So for my fourth flourish, you just finished periodic table, that chapter, right? So at O level, you are only focused on S block and P block. When you go to A level, you will delve into D block a lot deeper. So for fourth flourish, we are going to go on to it tomorrow when we talk about ligand exchange. Ligand exchange involves the transition metals in the D block. Okay? F block, you totally will not discuss it, even at A level. At A level, you will not do terbium, neodymium. That's complicated. All right. F block chemistry is only done later on when you move on to university and you happen to specialize in that kind of chemistry. So that kind of chemistry, by the way, SPDF block, the periodic table of elements to study every single element. This is the field of chemistry called inorganic chemistry. So in inorganic chemistry, we study all the elements except carbon. Because carbon is so important, carbon has its own family called organic chemistry. So organic chemistry is carbon-related chemistry. Everything else other than carbon in the periodic table falls under inorganic chemistry. All right. So as a undergraduate, okay, I took modules in inorganic chemistry all the way until I finished. That's why my modules will include things like we will go to the class. My lecturer will ask me, take out periodic table now. We took pick out. Today, we shall discuss the chemistry of silicon. I'm sure you all can find where silicon is in the periodic table. The whole 3-hour lecture is just silicon. Okay? That is the way university chemistry is like. The next lesson. Okay, today we will discuss the chemistry of germanium. Germanium is just below silicon, by the way. All right? That's why if you ask me, do I know about the elements? Of course I know, because I've sat through a lecture for almost every element here. Okay, F block will only come up when you go to very advanced chemistry, probably year 3 or even your master's year, but you start learning about F block chemistry. Okay, what kind of reactions will they undergo? Okay, now, but as a parting note before we go off, okay, what's interesting is when you get to D block, which is like titanium, 3D is the last subshell that you filled. Okay, titanium has 2 electrons in 3D, 3D2. Now, what's interesting about transition metals like titanium is that in addition to the 3D electrons, the 4s electrons are also considered their valence electrons. I repeat, in addition to the 3D, which you filled last, the 4s electrons are also considered their valence electrons, meaning if Mr. So wanted to make titanium lose electron, Mr. So can make titanium lose the 4s electrons and the 3D electrons. I repeat, titanium could lose the 4s and the 3D electrons. Okay? Meaning titanium can lose the 2 electron here. It can, in addition to that, lose the 2 electron here. So it can lose up to 4 electrons. That's why titanium forms 4 plus. Oh, why 4 plus? Remember we said just now, lose electron. Lose electron become positive. Because you lose the negative things in your life, you become positive. If I lose 4 electrons, 4 plus. But titanium need not lose all 4. Titanium can actually lose just 2 of the 4. Titanium also has 2 plus. So this, ladies and gentlemen, for 4 flourish, is the reason why transition metals like titanium display variable oxidation states in their compounds. They have variable oxidation states or different charges because they can lose a variable number of electrons from the 4s and from the 3D. Okay, so not just titanium, all the metals in the middle block, the D block, could potentially do that. I say the word potentially, yeah. Okay, so for example, for 4 flourish, if you go back to the previous page, I did iron. Iron is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. These are the electrons you are interested in. These electrons can all be lost in theory. Okay, in theory, all these electrons can be lost, but of course, it will lose a variable number. So, iron sometimes loses just 2 electrons. Okay, when iron loses 2 electrons, it forms Fe2+, which is coincidentally green in color. So, what is Fe2+? Fe2+ is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. The 2 electrons that it lost came from 4s. Okay? So even though 3d is filled last, the 4s electron is actually lost. All right? Next one. What is Fe3+ then? Fe3+ means you lose 3 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. So the 3 electrons lost came from 2 from 4s, 1 from 3d. And this is the variable oxidation states in their compounds, which is demonstrated by the transition metals. For 4 flourish, we just did QA, right? Fe2+ is green. Fe3+ reddish brown. You see, I use the colors some more. And we know the more stable form is actually Fe3+. Because if I leave Fe2+ standing in air, it oxidizes to Fe3+. So why? Why is Fe3+ more stable than Fe2+? One reason can be actually be found here in the electronic configuration. 3d5. What does 3d5 symbolize? You already know 3d, maximum 10 electrons. So what's so special about 5? Well, 5 is half of 10, right? So 3d5 means half filled subshell. Because it's a half filled subshell, it is also stable. So at A level, you will learn that a half filled 3D subshell is stable. So 3D5 is actually stable in comparison to 3D6. Okay. Now, is it as stable as neon and argon? No, it's all relative. So Fe3 plus is not as stable as argon, a noble gas. But Fe3 plus is more stable than Fe2 plus. Comparing, important to know what you're comparing against. So Fe3 plus is more stable than Fe2 plus because of the half-filled 3D subshell. Okay? I hope this is fascinating to you for fourth flourish. I hope it allows you to see what you are learning right now in QA in periodic table in a different, new light. And that is the point of Chemistry Olympiad, to allow you to see the current chapters that you are doing and seeing how things actually tie everything together. Everything is linked together. Okay? And for the 3 flourish students, in case you're wondering, my 4 flourish students, most of them had actually sat through this lecture before. Last year during SJChO Training, I used the same notes for this particular topic. So these notes are not new to the students. But why do they want to listen to it again? Number 1, revision of atomic structure. Number 2, hopefully, as you go through the pure chem syllabus at O level, you learn more and more chapters. You learn so many things to remember. But now, this is the chance for you to link everything together. Do you see how QA is linked to atomic structure now for flourish? I hope so. All right. And so how did Mr. So get all this knowledge? It's by learning and reading and reflecting every day. Every day I reflect and I learn a little bit more. Okay? I'll be honest, when I was your age, I never thought about Fe2 plus, Fe3 plus this way. Even at JC, I never thought about it this way. When I started teaching that, I realized, oh my gosh, actually that's true, right? That's why Fe2 plus oxidizes to Fe3 plus so easily if you leave it to stand in air. Because Fe3 plus has a half-filled subshell, which makes it more stable than the Fe2 plus. It's not as stable as a noble gas, but it's somewhat more stable than something like Fe2 plus. Okay, and with that, the final thing we need to do today is to poll. This poll is not anonymous. Okay, so I'm going to stop recording now first. Thank you. Stay here.